this is like, I don't have a conical pendulum. So this is kind of what it is, right? It's a pendulum that swings like this, right? So it is almost, it's this horizontal circle which has an angle theta relative to the vertical, right? And it just does this. And what's nice is it's an elegant piece of kit. It's very simple, and it allows us to do some algebraic proof to demonstrate how the mass of the pendulum on the end is kind of independent of the other variables at play. I'm not going to talk too much more about it here. I'm going to let you watch the tutorial video, which will go into what I've just said in more detail, and hopefully it helps you understand how useful this little thing can be. Okay, so let's take some time to talk about the conical pendulum, okay, and why it's at all useful, okay. Well, the conical pendulum, although it's very simple, okay, it looks just like this, where you have a tether point, a string, and a ball at the end, and it just moves in a nice horizontal circle. Usually you might have a clamp stand here, but for the purposes of this illustration, I don't have that. It's very simple, but it's quite elegant actually, because it allows us to demonstrate some pretty cool proof, which effectively shows us that the only two variables which affect the rate at which this ball is subtending its circle are the length of the string, okay, and the gravitational field strength, okay. It has absolutely nothing to do with the mass of the ball, which sounds kind of counterintuitive. You must kind of be thinking, well, surely the mass of the ball affects the rate at which it moves, but it doesn't at all. Okay, it's really odd, but the proof, the math shows it very elegantly. Okay, so I'm going to show you how we get to this derivation. Now, using our understanding of circular motion, centripetal acceleration, horizontal circles, you need to watch those videos if you haven't already to understand this. We know that the horizontal component of the tension force here, we're going to call that Ftx, which is also our opposite, okay, is going to be providing the centripetal force in this particular situation, keeping it moving in a circular path. And we know that the magnitude of centripetal acceleration is equal to mv squared over r. So we can say that the Ft is going to be our centripetal force, and that's equal to mv squared over r. Okay, so we can say that because this is the opposite to the angle here, we can say that the sine of the angle, okay, sine theta, multiplied by the hypotenuse, which is going to be our tension force, is going to be equal to mv squared over r. Okay, and we have that expression here. Okay, and that is the first half of our derivation. All right, and if we take that further, we can talk about the vertical component of our tension force, okay, which is going to be Fty, and that is equal to weight. Okay, the magnitude of the weight is going to be proportionate to the magnitude of the vertical component of the tension force. Okay, and we can say that because we're assuming that there is no acceleration in the vertical direction. Okay, and that is obviously our adjacent, and we know that the adjacent is equal to the cosine of the angle multiplied by the hypotenuse. So we say that the cosine of the angle multiplied by Ft is equal to mg, because that is equal to weight. We know that weight is equal to mg. Okay, and that's where we get this expression from. Okay, so what happens when we have the vertical and the horizontal component? Well, we can start putting them together. And if we express this as a trigonometric function, then we can sort of put the pieces together, right? Because we know that sine theta over cosine theta is equal to tan theta. Okay, so if we express this like so, okay, we say that Ft sine theta divided by Ft cos theta, we say that that is equal to the magnitude of the centripetal force divided by the weight. Okay, we say that this is equal to mv squared over r divided by mg, which is equal to tan theta. Okay, so if we know that this is equal to tan theta, because sine theta divided by cos theta is equal to tan theta. We can simplify it further, and we can divide through by m and multiply across by r, okay? And we can say that tan theta is equal to v squared over r times g. And in this, we can see that there's no reference to mass whatsoever. So what we're saying is the angle is not affected by the mass, okay? So the rate at which this ball subtends the circle is not related to the mass of the ball at all. It's related to the length, okay, of the string and the gravitational field strength, okay? And that's some really lovely proof that we've just demonstrated, okay? And what's even better is we can use this further still, and we can say that v is equal to the root of tan theta times rg, okay? And this equation becomes important later when we're talking about banked tracks and calculating centripetal force when banking is involved. That is to say, when something is traveling in a circle at an angle, okay, which might look something like this. You have your car and it's going round the track at an angle, like NASCAR, right? So that expression becomes very important then. But until then, that is where I'm going to end this tutorial for now.
Okay, so hopefully that tutorial has covered some important stuff. That final derivation, that equation at the end, rearrange for v, and what you can do is, if you have like a banked curve where the angle theta is anywhere between the line and the vertical component, you can actually use that to calculate the velocity of the object. It's really, really clever. But you have to be careful where that angle is. We'll talk about it in another video. Please like and subscribe. It really helps us grow the channel and get more quantum content to you guys. But in the meantime, I'll see you next time. Bye guys.